Hello, everybody. I hope everybody had a good holiday weekend. Really nice weather. Right before we started the recording, there was a question about that announcement that I sent out this morning. You might remember that the School of IT here at Sellersburg, we have our own network separate from the Ivy Tech network. And a couple weeks ago, something went wrong, and apparently all the accounts got erased. So it became necessary to set up accounts, I guess. You'll need to log in and set up your account, even if you already had one in the past. Or if you haven't done so yet, the temporary username and password for guest is going to expire on Friday, I think is what it said in the email. So you might want to do that sooner rather than later, or there won't be a guest password to log in with. And you can find all the information for that on our Ivy Learn site. Or since everybody in this room is heading into an IT field, most everything in IT can be handled remotely across the internet, but remote access does behave slightly different than being there sitting by the machine. So it's a good thing to practice. So even if you aren't going to use those labs, it might not hurt just to get a little bit of practice logging in and seeing what remote access is like, doing some things on accessing a computer across the network rather than sitting directly at the computer, because that is a skill that you will most likely need when you're out there working in IT. And for the remote access, they use this software called Beyond Trust. If you go to our site and do modules, which is taking forever because of the Zoom call. There was an update on Zoom today, and I was hoping that things might run quicker on the latest update, but it doesn't seem like it. Seems like it's still going really slow. So you all don't have this.
No, it just had a. I was just gonna make a joke. I was saying no, of course it didn't. It didn't fix anything it actually needed to. It just added emojis.
Oh, okay. Oh, that's important. Yeah, we need emojis in the chat room. That's an important part of the English language anymore. But here under the section for resources on modules, you'll see this one for video lectures, which there's not really much posted there yet. I saw something in the chat room and I was expecting some of the new emojis to show up. It seems to have changed the font on the names. Everybody's name is written in a new font now, but it's not that much different than the old one. And all the way down at the bottom, here's the temporary login and password, the ones that expire on Friday. So you have until Friday to access them with that. And then when you log on to the machines, there's a little icon. One of the desktop icons says SOIT for School of IT. And when you click on that, it might say SOIT Help Desk. When you click on that, there's step-by-step instructions to set up an account. There's the new emojis. And I made a little video, but the written instructions are straightforward. There's the link to them right there. It's basically just click this link right here and make sure you use SAML login, not the typing stuff in. Just you have to use the SAML authentication to actually get to Beyond Trust. But should be straightforward. If you haven't set up an account there yet, you'll want to do that before Friday. Or if you used to have an account, they all got erased, so you'll need to do that before Friday. And yeah, or it's just generally a good idea to practice remote access. is you will probably need that somewhere in your IT career, and it's not exactly the same. It's very similar, but certain things don't work. Like that thing I was just talking about, the resetting accounts. I can't reset mine because I have a regular Windows 10 account on that. The faculty all does, which means we have to hit Control-Alt-Delete to get to the Windows 10 reset password. And that's something you can't do remotely. Because if you hit Control-Alt-Delete, that's going to be on the computer you're sitting at, not the computer you're remotely accessing. So there are slight differences like that might be good to practice. But I guess for tonight, we'll get started on tonight's material. There were a couple pieces left for talking about binary code, and this is the class where we really cover them, so I kind of wanted to talk about that. And then we will get into selection structures. And then this week and next week is pretty much all programming stuff. So we'll be doing everything in Raptor and Python. And then I think there's another math section to talk about concepts again in like weeks in module 6, I believe. There's one more of those, but the next couple weeks are programming after we finish this binary code stuff, because this is the class where it covers, or where it gets covered. One thing that I wanted to note when I reviewed those videos, there at the end, we were going over the 2's complement and kind of doing the math for it. I think the numbers in the videos where we took 13 and 4 and did the 2's complement to get a negative. And when we subtracted it in binary, we had that extra bit. And then we got a 9. Oh, when we subtract 13 minus 4, we get that. And then we have this extra bit that's a 1. And if we go the other way in 4 minus 13, we ended up with a 0 in that extra bit, and then the 2's complement of 9. And I noticed in the video, I didn't really explicitly state it, but you might have noticed that when we were up here on this side of the equal sign, like beforehand, we defined a 1 to mean plus and a 0 to mean negative. But then after we do that math, the 0 means negative and the 1 means plus. So if you're actually working in binary code, things like that show up a lot. And you have to kind of know what machine you're working on to deal with little things like that. Just a subtle one, but I noticed it in the video and I didn't, thought it might be a good explanation, and it seemed like a good segue into what we were doing a week ago after the 3-day weekend, after the 3-day weekend. That was a long time ago, right? A really nice 3-day weekend too. So I hope everybody enjoyed it. But we saw how we represent positive integers and talked about floating point numbers in very similar fashion. And then we went into the positive and negative stuff, the sign and magnitude, which just throws a symbol on there. There's still a lot to do math with. And then we led into 2's complement, which is how the machine is actually doing math, what the component is doing for it. Yeah, I see in the chat room comment that's not confusing at all. But yeah, working in binary is kind of confusing. That's why we simplify it, try to simplify it when going over it. And we call everything on and off. And I may have been trying to avoid that subtle change, because remember, that's going to be electronic components. So I know if I have one of my favorite hobbies is to put together electronic stuff. I really like to try to make new input devices. So whenever I have something going on with a full adder, I immediately invert that bit so that it's back to the 1-0 thing. So there's electronic component. It's probably fixed in electronic components afterwards, but it just wasn't really specified in that video, so I thought I'd mention it. Well, we saw that. That's how the computer actually works with. So we're actually using 2's complement. And another one that we might use some, I'll kind of go back to base 10. It's something y'all have seen before. Maybe we have a number like 3,900,000. Let's make that billion. 3,900,000,000. And we're talking about something up in the billions, so we tend to ignore those rest of those zeros, and we're mostly concerned with the ones way up here. And having all those zeros mean, well, that's a place that we're likely to make a mistake when we go punch things in the calculator, right? If we have to hit 0 a whole bunch of times, there's a good chance we could miss it. We have a more concise way of writing this in our regular base 10 numbers. All right, the little 10 subscript to indicate definitely a decimal. So usually when we're in base 10, our normal numbers, we might use scientific notation for a big number like this, where we take just the important digits, or significant digits, one we know are definitely there, and move our decimal over to just one spot over. So we have one non-zero digit and then our decimal to kind of make things a lot easier to write and enter in the calculator. And then we'll say times 10 to some power, which in your math class, they probably told you to count it, right? Like 1, 2, 3, 4, 5, 6, 7, 8, 9. So we moved our decimal 9 places over. 4, 5, 6, 7, 8, 9, and then stuck the decimal there. But we were talking about all the way back to columns again last week, right? We had the 10 to the 0 power, 10 to the first and second, third, fourth, fifth, sixth, seventh, eighth, and then ninth is here. So another way to look at that exponent is that tells us this decimal is actually we're looking at something in the 10 to the 9th power column. Everybody seen scientific notation before? Kind of remember doing that? Or a similar thing with really, really small numbers? 0, 0, 0, 2, 7. If we have something like this, again, when we go punch that in the calculator, pushing 0 that many times is a spot where a mistake is very easy to, it's very easy to make a mistake and not push enough zeros or push too many, or it's a lot to write. It makes it hard to read when we see all those zeros in a big long number, and those zeros don't really matter much. So we can also move our decimal over this way, write down just our important bits, 2.7 times 10, and well, here we moved to the left, we moved in the positive direction, and we got a positive number. And over here, we're moving to the right, and you might remember our columns was like this first one's the 1 over 10 column, which we can also write as 10 to the negative 1 or 10 to the negative 2. So we end up with negative exponents going this way. So when we write the exponent, how many was that? 1, 2, 3, 4, 5, 6. We moved to the negative, we moved our decimal to the negative 6th column. The 1 over 10 to the 6th column is where that's at now. And there's different little tricks in math class. You probably heard about counting that, but does everybody remember seeing scientific notation before?
Yes.
So we can do the same thing in binary. I'm just going to pick some random one, and there's a whole bunch of zeros there. So we can kind of write it the same way. Let's put a 1 times, but we're in powers of 2 this time, and our original decimal point would have been way over here, and we move that 1, 2, 3, 4, 5, 6, 7, 8. 8 columns over. So it kind of means the same thing, just with a power, just with a power of 2 rather than 10. And same thing when they get small. In particular, when they get small, it's a little different. So if we had something like 0, 0, 0, 0, 1, 1, just to avoid writing too many, we can move our decimal 1, 2, 3, 4, 5 spots over and just write those ones that matter. We could say like 1.1 times 2 to the negative 5th as a more concise way of writing that number. And then it's just implied that all those zeros are there. Just like over here in the 3 billion, it's just implied that all those zeros are, we know all those zeros are there. So we don't necessarily have to write them. Makes it a little bit easier to work with. And this is another thing that computers kind of do when they're working in binary. Is it okay if I erase these numbers? That was hopefully just a reminder.
Yeah.
Scientific notation, and then just like everything we looked at last week, if we can do it in base 10 numbers, we can do it in base 2 numbers as well. There's nothing special about using 10 to represent our numbers, except that we have 10 fingers, so it's convenient for humans. So there's something, a common way of representing numbers like that is often referred to as offset binary. And I'm going to put quotation marks around that because that's something people often say. Our technical term for it, without quotation marks, is excess K. And usually K is a number. So like on a Windows machine, it'd be the excess 127 system for Windows. And it represents some sort of a binary exponent. And the idea of it is that we always have that in the exponent. So, for example, 1 times 2 to the 7th. I'm going to write that in the regular notation. So there's a 1 followed by 7 zeros. We can write that in this excess K notation. And what this means is we kind of have this times 2 to some power thing always there. And we automatically assume it's to the 127th power. And then if it's bigger than that, we'll add bits, or we'll add a positive number to it. And if it's smaller than that, we'll add a negative number to it. So yeah, you might remember in 8 bits or 1 byte, we can store 256 values, which takes us from 0 to 255. But then if we need to include negative numbers, we have to shuffle that down 1, and then we can go from negative 127 to a positive 127. So that's where the 127 comes from. On a Windows machine, it uses 8 bits to keep track of this times 2 to some power thing. And that tells us where the decimal point is actually supposed to be at. So if we had a number like 1 times 2 to the 7th, what we would do is it's a positive exponent, so we would add it to 127, and then that goes into the binary. So 7 plus our 127 that's kind of offset, the offset starting point, gives us 134, which in binary is going to be 128, which leaves 6 more to go. So we don't have any 64s or 32s or 16s or 8s. Then we'll have a 4, a 2, we won't have any 1s. So there's 134 in binary. Then we tack that on to the 1 or the 0 that we had beforehand. So that would be how we roast that number. 1 times 2 to the 7th is we put 1, followed it by 134, And the computer is going to know it's working with the excess 127. And K could be any number. We could do 64. We could do excess 1024. I just went with 127 because that's what Windows machines use. And I think most people are probably using Windows 10 here. But we have this offset so that we have this big number, and then we have a couple of bits. I wrote a 1 there. We might have space for more bits, but we have the significant bits, and then a second set of 8 bits saying exactly where the decimal is supposed to be. And that's something that computers regularly do to keep as the numbers work their way through, because it allows for bigger or smaller ones. And we're not going to get into doing math with those. I just wanted to talk about it because it's something that computers really do. And some people are going to be using binary code, so we want to talk about it. I guess another one we could do would be like 1.1. That's supposed to be in binary. 1.1 times 2 to the -5. And in that case, our exponent's -5, so we add that to our offset. So -5 plus 127 gives us 122, which then we actually need in binary here. So we don't have any 128s. We'll have a 64, and 32 makes 96. Plus 16 is 112. So we have an 8, which then gives us 120. So no 4s or 2s. Yeah. So there's 122 in binary. And that the computer's going to know that that represents the offset, where the decimal is actually supposed to go. And then we still have, in this other part, that 1 digit. So that's something involved in how computers actually keep track of numbers and what's actually going on inside of them. I wanted to make sure and mention it because some of us will end up spots where we're actually working in binary code regularly. I wanted to talk about that. So that, well, it's already a scientific notation that you might remember from your math class. Computers can do that as well, and we usually pick a middle point and we offset the exponent by that much, and then we add or subtract from it, and that way we only go down. The smallest that would be a 0. So we only go down to a 0, which means the decimal's already in the right spot. And computers, that's something regularly used in computers. A question that I've heard before is, how does the computer know when to do this? And the computer always does this. So anytime a computer is actually storing a number there, running it through the CPU or pulling it out of RAM, it's going to be doing it in this thing that's sort of like scientific notation. And 2's complement. So those are the 2 that are actually running through the machine. And once again, we have to know the machine we're working on in order to know what the offset's going to be. We're not really going to do any math with this because that is a little complicated, but hopefully that makes sense. It's scientific notation so that we can store really big numbers or really small numbers. And this value is just always there. And if we don't need to move the decimal, then we end up with a 0 in that spot. So that's something the computers do. Oh, is it okay if I erase this? I just wanted to briefly mention that in case it shows up in your future somewhere, you'll have an idea of what's going on with it. 2's complement with offset binary is how computers really do math. But that's not the only thing computers do, right? For example, if I look at the screen right now, I'm looking at a whole bunch of thumbnails that have everybody's name on them. Well, nobody on the screen right now has a number in their name. So the computer must be doing something different for those values, right? And for that, we use ASCII or Unicode. So ASCII, the A stood for American. That was the original one developed back in the 40s. Had all the symbols we need for the English language. However, English isn't the only language in the world, right? If we start to consider other around the rest of the world, there's still some symbols missing when we have only the symbols needed for the English language. So that was extended up. So ASCII takes up 1 byte. Will represent things with 1 byte of data, 8 bits. But that's not enough for all of humanity. It's fine for America, but not for the whole world. So we expanded that up to 16 bits so that we can store a lot more information that way. And the first 255 values in Unicode are ASCII code. So it's an extension of it. So you search either one of those. This is inside of this, so they kind of go together. But since we are in America, you will often see it in reference material referred to as ASCII code. But Unicode is just an expansion on it that has the rest of the symbols the world uses. And the idea is we just give each value a numeric representation. So like a capital A is the number 65. A capital B is a 66. We can go through the alphabet that way. And then finally get down to our lowercase letters. So like a lowercase letter, A is 97. And lowercase b is 98. Go through the alphabet. And similar thing with our digits and the exclamation marks, punctuation, parentheses, commas, every other symbol we use. We just give it a numerical representation, which you certainly aren't ever going to be expected to memorize. So we just check charts for things like that. And then we can convert back and forth between things on the chart. I'm going to write the example on the board first. So to see things like this, maybe we have those words. Hot summer, which was on my mind as something that's not too long, because I guess somebody did a remix of that classic Prince song, because I keep hearing it on the radio. It's like, it's strange for this to get played that much unless it's a new version, and it's been 20 years since I heard the old version, so I can't tell if it's a remix or not. But say we have those words, and we want to know how the computer's actually storing. It's going to be letter by letter. Oh, and that's a string. I should put quotation marks because we talked about that before. Our variables and numbers do not get quotation marks, and we'll be back to programming here in about 20 minutes, probably less than 20 minutes. Just kind of going to go over the process here. So we have those words, hot summer, with a space in between them. So the computer is going to store each one of those as an integer in binary integer like we saw. And to translate it, we would just check a chart or use the tools. There are lots of digital tools, pieces of software that will translate it for us, but we can just kind of search for an ASCII chart or a Unicode chart. Either one would work. ASCII is the first few numbers. There's lots of charts. I checked just a little while ago. This one had a nice little table. Most textbooks do, but our current textbook doesn't for some reason. So the first 32 characters, going from 0 up to 31, those are control features. So like a 6 represents acknowledgement. There's some bell sounds. The ASCII number 9 is the horizontal tab. That's what happens when we hit the tab key and our cursor moves over a little bit to indent a paragraph and stuff. That is just ASCII code number 9, which some of y'all may have already discovered in Python, that is very different than pushing space 4 times. They're not interchangeable. We can use either one, but we can't use them together. There's also a vertical tab, which doesn't get used much anymore. It used to be important on typewriters many, many years ago. But things like a line feed and a carriage return and all the control functions are in the first 31. And then we start with number 32 is the a space, then exclamation mark, represent a numerical representation of a quotation mark is 34. And we go through all our symbols that way. So to translate that sentence I wrote on the board, we would look for, well, it starts with a capital H. On here, capital H is 72. So we just need to know what all those numbers are, like 72. And then we have a lowercase o, which is 111. And then a lowercase t, I'll put this one on here, is 116. I'm going to stop the screen share. But we would just go through a chart like that and get all our values. Then a space is number 32. And to speed this up a little, I already have them in my lecture notes, so I'm going to use this. Then a capital S is 83. U is 117. We have two 109s. 109. E is 101. And a lowercase r is 114. So we would just get all these numbers and then convert them into binary to see how the computer actually stores them. And you might remember the other day when we were talking about hexadecimal, the point of hexadecimal is it makes our conversions easier. If we have a decimal number and need to get binary, it's quicker if we go through hex first. So if we take 72 and divide by 16, what do we get? 16 will go 4, gives us 64. So we have 4 with a remainder of 8. So in hex, that's 4, 8. And then from hexadecimal, we can turn those into 4 bits at a time. Each hex value is 4 bits at a time. So the people that regularly work in binary code end up working in hexadecimal, because then we can work in at 4 bits at a time. So a 4 is 0, 1, 0, 0. And an 8 is 1, 0, 0, 0. So that would be the representation of 72, or 111, which I have a calculator, just grab the calculator here. So if I do 111 remainder division by 16, you can see it gives us, I can find this spot. Y'all see that on the screen? I don't think it's coming through very clear. This calculator does remainder division, but 6 with a remainder of 15. So that would be 6, and 15 is an F in hexadecimal. And then we can turn those right into 4 bits at a time. 6 is a 0, 1, 1, 0, and an F is, well, the highest number we can store in 4 bits, so it's all ones. And I think y'all can kind of see where the process is going there, right? Does anybody have any questions about that? You can see it's just a little time consuming to find those numbers and then convert them, but it's a one-to-one correspondence. So all we're doing is conversions. Look up a letter on the chart, get that number, then convert that into binary, and that's what the computer is actually storing. So that's how we store our pattern. Yes.
Is it the ASCII? Is it a standard like chart? Like it's not gonna change per, like the number values aren't gonna change. That's just what they are. So I can look up and use like and print an image of one, and it's not gonna be a different chart rather than like a different chart.
That,
All of the charts are
that
the same.
they're all the same.
Okay.
And that word you just used is the S. So it's American Standard Code something interchange. I have to look up what it stands for again. But yes, it is standardized. Share my screen. What does ASCII stand for? I haven't looked it up in a couple years, and I'm forgetting what one of the I's means. Which hopefully it's not going to take too long. I bet it was on that page I already had pulled up. Oh, there it is. American Standard Code for Information Interchange. So it is standardized. It will not change. If you're, and when you do that, make sure you look through a couple charts because some of them are harder to read than others. If you see some, there's a couple charts where they found nice ways to condense it, but they might not exactly be intuitive. So like condense all that information that fits on like a business card thing that fits in your pocket, makes it easy to keep track of. The chart might not be intuitive to read. So if you look up some charts, I think was that you that asked Larissa?
Yes.
If you look one up and you like the colors on it, but you're not sure how to read the way they set it up, just let me know and I'll show you how to read those. Because there's this kind of strange a way to combine columns and rows to really make the charts very, very small. So they take up very little space. But that is a definite yes to your question. It's always the same. And going the other way is very similar. I'm going to erase the board. Is that okay?
Yeah.
I think we really need to finish the example of the points there, right? Y'all can see what to do, and that it is just a time-consuming thing when you need to do it. And the main thing was just to show how that is stored. But to go the other way, I have one on my notes. So maybe we have 0, 1, 0, 0, 1, 0, 0, 1. They're all 8-bit things. And I started erasing because it's not going to fit. I'm getting ready to write a bunch of binary code on the board. I need a whole bunch of room. So 0, 1, 0, 0, 1, 0, 0, 1. 0, 1, 1, 1, 0, 1, 1, 0. 0, 1, 1, 1, 1, 0, 0, 1. That'll work. I had more wrote on here, but y'all probably guess what this says really quickly. So in the situation, we'll know the context we're at. Just like that thing I've said a couple times last week and then a couple times tonight. You kind of have to know the machine you're on, and when you're working in binary, which means you'll also know the current context. So when you see this, you would know that you're looking at ASCII code. So we just need to figure out what this says. And go from binary to decimal, it's quickest to go through hex. 0, 1, 0, 0 is a 4. 1, 0, 0, 1 is a 9. Which then 4 times 16 is 64, plus 9 would be a 73. And base 16, so 73 and base 10. Then the next one, we split it up in groups of 4, and then each one of those 4-bit chunks is a hex value. So 4 plus 2, 6 plus 1 is a 7. 4 plus 2 is a 6, which 7 times 16, I don't know off the top of my head like I do 4 times 16, but 16 times 7 is 112 plus 6 would be 118 in decimal. You see how that, it seems odd to go to a different system to get to the one we want, but it cuts a lot of steps out because it relates directly to the binary, and then we have a lot more symbols in our columns, and humans can deal with way more than 2 symbols. Then over here, well, there's a 7 again, and 1001 is a 9. So 112 plus 9 will be 121 in base 10. So then once we have those values, we can look at the chart, which I just closed for some reason. I'll open it back up. I don't know. Yeah, I went to close the tab next to it and closed all the tabs, which is a little inconvenient on the Zoom call with everything slowing down. But if I hit Control H, I should be able to get right back to that page really quickly. There we go. So the first one there was a 73. So if we find 73 on here, it looks like that's a capital I. Can you all see my screen? See what
Just the little one.
118. So if we find 118 here on the chart, looks like that's a V. And well, ASCII code goes in alphabetical order, so we could just count up the next couple letters to get 3 letters after that. We all probably already guessed what that's saying anyway. So we have I, V, and then 121 is ASCII code for a Y. And in my notes, I wrote IV Tech, but that made a great really long string of 1s and 0s. I filled up the board with just 3 letters. So you can see the process is straightforward. We have our number, we figure out what that number is, and then check it on the chart. Or to go the other way, we find it on the chart and then convert that to binary.
I have a question.
Yes.
I don't really understand what the 16 going to 10 is. That's not really clicking. What is that again?
So this is base 16 hexadecimal. That's a hexadecimal number. So we have a 16 to the 0 column and a 16 to the first column. And then those numbers could get bigger if we needed, right? 16 squared, 16 cubed. Does that make sense from what we were talking about last week?
Yeah.
And that way we can, instead of having a whole bunch of things to translate, right, if we go through this, we have to go through all these columns. So there's no 128s, then we have a 64. Don't have any 32s or 16s, then an 8. No 4s, no 2s, and a 1. So we have a whole bunch of columns. But if we switch to base 16 first, then we only have 2 columns to deal with. So we have a 4 in the 16 column. So we have 4 times 16 plus 9 in the 1s column. 9 times 1 is how represents that number.
Okay, yeah, that makes more sense.
Okay, you can also go right from binary if you prefer. This just kind of shortcuts it because humans our minds can deal with a whole lot more than 2 symbols. It seems confusing because 2 symbols just isn't enough for us. We can easily deal with 16 symbols at once and cut it down to just a couple columns. So a shortcut on the conversion, cut out a couple of steps.
Okay, gotcha. All right. I was like, wait, why is it separated into two and why does it go from 16 to 10? And my brain just didn't connect.
Okay.
I'm tired.
So in a base, since binary doesn't really work for us, we need a bigger base. So if we just, but we want it to work really, really well with binary. So if we just start checking the powers of 2, 2 squared is 4, and we could handle more than that. So if we square that again, it gives us 16. So 4 squared gives us a good system to work in. So we can handle a lot better than binary. And since it's all 2s, it's going to relate directly to binary. In essence, it's 4 bits, because the 2 squared, the 4 bits to some power gives us a hexadecimal column. So whenever we have 4 bits in base 2, we can immediately write down the hexadecimal symbol for that. Any other questions?
Nope.
Okay. And does the stuff there about ASCII code make sense? It's a little time consuming. You can see it fills up the board very, very quickly. But
Yeah, it makes
the
sense.
the process is fairly straightforward. It's just look the number up and check against the chart. And that covers most of the ways that computers will store binary code. For the most part, we're working with 2's complement and that offset binary, which is sort of akin to scientific notation, or it's very akin to scientific notation. You might remember from math class, to keep track of where the decimal point actually goes, or ASCII and Unicode, which gives us another way to store values. Like that's a fairly famous number, right? We learned about that way back in elementary school. We also learned that it's an irrational number. Those digits go on forever on that. So kind of hard to fit that in a finite number of bits, right? So what we use is, it's often referred to as big integer or big decimal or big floating point numbers. Some textbooks call it binary coded decimal. And basically, instead of storing that as a binary number, we store it as a string. We store those symbols. So it's ASCII code for the digit 3, then ASCII code for the dot, then ASCII code for the 1, ASCII code for the 4, and so on, and however many digits we want. So there's a website where you can go download pi to a trillion digits, and what it gives you is a text file. And then we know they are all digits. So then when we go to use that big number, big integer or big floating point number, we know they're all symbols, so we can do digits, so we can do them all in 4 bits. And then we do the calculation of what it is on the fly at runtime, instead of actually storing the number as a binary number. So that's the other way that'll show up as well, where we can just store really big or really any size number just by storing the symbols instead of the numerical values. So that shows up in there as well. And that's pretty much what I wanted to talk about on the binary. I also had notes when I pulled these out the other day. I thought we were going to have Monday to talk about it as well. So I had notes about error correcting codes, because problems happen, right? It happens. Our modern world, everything's connected. Right? Y'all are attending class right now across the internet. So data is being transferred, and little errors can creep in if we're sending a bunch of 1s and 0s through wireless signals, down lots of cable, and then through another Wi-Fi signal, there's a chance that one of those ones or zeros could get messed up from background interference or something. So we need ways to detect errors. Typically for networks like that, small, the internet or other local networks will check parity, which if you haven't heard that word before, parity refers to even or odd. Because if we add all those bits together, all those zeros and ones, we're either going to have an even number or an odd number. So maybe for some particular network settings, the computers are set to know that everything that comes in should be an even number. So that if our actual data, all the ones add up and give us an odd number, we add a 1 on the beginning for the parity bit. And then we have an even number. Or if all of our data, we add up all those ones and zeros and get an even number, then we throw a 0 on for the parity bit because we don't need anything else. So then when we transmit that data, the computer knows, well, it'll check that and be like, oh, well, I was expecting an odd number of ones and this data has an even number of ones, so something must have went wrong. And here on Earth, that's no problem. One of the core ideas of the TCP protocol, which our modern networks are mostly based on, is that we're just transmitting around the Earth. So we check for an error, and if something went wrong, the computers can be like, oh, something went wrong, send it again. Something went wrong, send it again. And anytime you've ever had to wait on a web page to load, like if it seems like the little thing's spinning more or longer than it should be, that's what's going on. The computers are just going, oh, something went wrong, send it again. Something went wrong, send the data again. Sometimes it takes a few tries. But that wouldn't really cut it in other situations, right? Like some of the things NASA's involved in. Or for an extreme example, that camera that we sent to Pluto a few years ago, the New Horizons probe, when it got to Pluto, it was taking 4.5 hours for a signal to go each way. So something went wrong, send it again, isn't really a viable option in that time. So we also have a way of putting together binary code, which if you can see from the label on those notes there, the error correcting. We can put together codes that will correct themselves. But that was just an extra thing I wanted to talk about. I'm pretty sure I have that on a video from where I've shown it in previous classes. So I will see if I can dig up one of those videos, but I'll put the link into our Ivy Learn site if you're interested in that. But we can adjust the way we encode stuff and put together codes that will actually correct themselves if they come through messed up. It's kind of an interesting concept. That's why I wanted to cover it. But when I pulled the notes out, I thought we still had a whole nother day to talk about that. So I want to kind of move on to the next topic. And I'm almost positive I have some videos from the last time I taught this course going over that. So that'll kind of wrap up talking about binary code. Does anybody have any questions about binary?
Nope.
Oh, what's in the chat room? Try S42AC. You want me to put that in binary or in decimal? I saw that in the chat room. Oh, that was one of the questions on the quiz, wasn't it? I think they said the 2. What is the value of the 2 in there? Is that what that's referring to in the chat? So it's a base 16 number. So we have a 16 to the 0 column, 16 to the first, 16 squared. So it looks like we have 2 times 16 squared. 16 squared is 256. So 2 times 256 should give us 512. Is that what you were asking about in the chat? And then to get the whole number, 16 cubed and 16 to the fourth, we would just take and add up each column, which would probably involve a calculator, right? So we did F is 15, and that is in the 16 to the fourth column. So I'm 16 to the fourth plus 4 times 16 cubed, which is going to take up a bunch of room, but you see on the calculator kind of how that goes in. We just add up the value of each column, and for a couple columns, it's really big like that. Or to go to binary, each one of those hex digits is 4 bits. So F is 1111, 40100, a 2 is 0010, A is a 10, so 8 plus 2 is 10, B is 11, C is 12, so 8 plus 4 is 12, there. So that would be to go to binary, we just, each hex digit goes to 4 bits, or to go to decimal, whatever value is there. So like F is 15 times 16 to the fourth, whatever that number is. So that would probably go in a calculator. Then 4 times 16 cubed. That make sense? That'll kind of wrap up the math stuff.
Yes.
All right. And yeah, whenever I saw that there, I remembered that quiz from last fall. I think it was the last time I taught this course, maybe the time before that. But that question has confused people before, because they started adding up, trying to get the whole number or trying to figure out what it was. They just wanted that one digit. Like what is the value of the 2? And that would be 2 in the 16 cubed column in that case. Did anybody have any questions about the quiz, by the way? I do go back. Okay, I do go back over there, over those. Since I didn't write that quiz, I go back over the break points. What was the question you had on it?
So like some of the questions towards the top, it was written like 45 to like the power of 5, but it was asking about the base. And I just was just like, oh, it, whoever made it or whatever, they don't know how to put it like as a subscript.
So that question was for that the other meaning of those numbers, because we were talking last week about base numbering systems, like base 10. We have 10 raised to some power in columns for that, right? In first, 10 squared, and that is what the word base actually means. So you may remember seeing that in a math class before. If we have some number raised to a power, the number is called our base, and then that power is the exponent. So on that one, the base of 45 is raised to the 5th power. That makes sense, Larissa?
Yeah, I got the question correct. I just thought it meant that it was like, it just didn't. It wasn't written the right way, but I got it right. So.
Okay, yeah, it was wanting just the meaning of the word base, not base numbering system. But yes, I think a few people probably do usually see 5s there. Since we normally use a 10, if there's nothing written there, that implies 10. Kind of like the logarithms, like log base something of a number. The base is our little number, but if we leave that off, that implies that we're using base 10, because that's what's normal for units. you have other questions? Or just the one?
I had another, sorry, I had another question. Can we, do you just want me to share my screen and like show you? Cause I'm not sure if I like myself just got it wrong or if there was a way that I wrote it wrong.
That happens sometimes too. Yeah, if you want to share your screen, I can take a look at it. And also, I didn't write that quiz. So anytime that there's a quiz that I didn't write, I go back over them. But it was only due a few minutes ago, so I haven't gone back over it yet. I was waiting until after the due date to look back. So there's probably some points coming back. The 12 base 10 to a 4-bit binary. Oh, so that one is a formatting thing. You just needed the 1100. You didn't need to explicitly say it was in base 2. Since there's not a good way to type the subscripts in there, it just wanted the 1100. So you'll definitely get that point back. And I will probably do that this evening, kind of go over those and look at the and put points back on. I don't ever take points away when I do that if I don't agree with the question, but yeah, usually if I don't write the quizzes, I tend to find that I may not exactly agree with what the answer key says sometimes. And when number things like that, there's usually formatting issues. Because computers can only make exact comparisons. So yeah, there was one on there that I changed. I think 1 or 2 people had already taken the quiz, but the answer key had a space in there. Can't remember what the number was. It was like if the answer was a 2, the answer key had space 2, which we just talked about ASCII code. So the computer was looking for that ASCII code number 32, and then the number 2, followed by the ASCII code for the number 2. But people just wrote 2 because that was the answer, and the computer didn't see that space beforehand. So I do go back and check for things like that. Any other questions about that quiz or last week's homework before we move on?
Nope.
Okay. Yeah, I was getting ready to say, I assume the silence means no. What time is it? 7:05. Okay. We just enough time for a little segue here. So that picture that I said we'd return to a couple times this semester. When we started out this course, what was expected is that, the computers get input and output. And we've already kind of replaced some of those symbols because we know the international standard symbol for an input and an output is a parallelogram. So we know that computers are going to get some sort of input, end up with some sort of output afterwards. And something happens in between. And we started filling in this gap a little bit, right? We have volatile storage or random access memory for the most part. Volatile storage where we can keep things. And that's about all we've seen so far, right? But we could store some value and to do math with that value. But we've seen our volatile storage symbol for things that we need to keep around in RAM, and talked about the sequence. We move from our input to whatever those values are to the output. And there's that sequence that the program flows through, because machines aren't intelligent. We started calling some of them smart machines, but they're when you go to program them, it becomes very, very noticeable that they are not smart. So the first thing we have to do is have a sequence for the steps to follow, an algorithm. The technical definition for algorithm is a finite set of steps necessary to carry out a given task. the instructions to do something, and we need an order for that to go in. But that's all we've seen so far, right? We have that order to go through. Our flow charts at this point have our start point, and then they flow down, and well, we'll have some stuff going on, but the flow charts all look like a straight line. They just flow down, right? Not a very interesting program. It'd be nice if there was alternatives, right? Like after we got this first value, make some sort of choice about what math we're going to do on it for the output, right? Like that first week's homework assignment, or the second module's homework assignment, one of their after assignments was to do some math. We got a number and then we added that number and subtracted it and did all the math. But it'd be nice if we had a choice. So then once we got our numbers from the user, we could choose whether we wanted to add the numbers or whether we wanted to multiply the numbers, and let the user make a choice so that it didn't just do the same thing every time through. There was some variety. So that's the next topic for tonight and Monday. And that's going to be selection structures, which, since the rest of the UML stuff is up here, we'll use a diamond to represent a selection. So then our kind of general picture here, what's going to happen is after we get some value from the user or some sort of input from the user, we'll flow down and then we'll check that with a yes or no question. So that if the answer to the question is no, we'll take this path to the output. And if the question is yes, we'll take a different path. And that way some variety can happen. And probably do that more than once. We'll be doing that more than once very, very soon to keep it more interesting. And branching structures is another name for it. So instead of our flow charts, a vertical flow chart that just looks like a straight line, we'll be able to branch off. We'll have that starting point, and then we'll come down and kind of split off in different branches. And come down some more, split off in more branches, or split off up here, come down, split off here, and we can make take lots of different paths between our start and end point so that more interesting things can happen. So that's the next thing to talk about, which is also one of those items in that list of 4 constructs we need to solve any problem. We need a sequence for it to go through, and we need a way to make decisions or make selections. So why don't we take a break real quick, and then we'll get started talking about selection structures. Does 10 minutes sound good to everybody?
Yep.
All right. I could really use a cup of coffee. So again, I've got the necklace microphone on, so I'm going to mute my mic and pause the recording. But if you have any questions, I'll still be able to hear you. It's just these microphones are really, really loud when I'm drinking coffee. So I will see you all in a moment, 7:11. So we'll get back to it at 7:21.